This video is about Unit 2 computer structure, and we'll start off kind of summarising what we should know a bit about the 5-box diagram of the processor and how data is sent into the processor from input devices, it's sent out from the processor to output devices, and sent two ways between main memory and backend storage, because it needs to send data out to store long term as well as read it back in. Go over the three parts of the processor, which we need to remember: CU, I love you, right? To try and remember the three parts for an acronym. So the CU stands for the control unit, and its job is to control all the other parts of the processor. It makes sure instructions are carried out in the correct order, and you're going to learn more about the different lines that the control bus can use to do that. The ALU, I love you part, stands for arithmetic logic unit, which carries out arithmetic operations. It performs logical operations, and it makes decisions based on logic. Logic being things like and, not, and or. The right is the registers, which we should hopefully remember that are the storage locations inside the processor. They are used to temporarily hold programs and instructions whilst being executed, which takes us onto the actual diagram that you need to know about. Now, you won't be asked to draw this in the exam or anything, but you'll need to know and understand the various different parts that are on it. Now, if you look up the read and write videos, it goes into this in a bit more detail. So, buses. What are buses then? Well, they're simply sets of wires that connect up the processor to main memory and input and output devices. And you can see here there's only two that we really need to know about. The first one's the address bus. Now, if we pay attention to the arrows here, you can see the processor only sends out data on the address bus, but the data bus, it goes in two ways, and that's something we're going to get into in more detail in a second. So the first bus, the address bus, then its job is purely to carry address info from the processor to main memory and other devices, and they'll call that unidirectional. It only carries data in one direction. And there's a little bit more we need to know about it in terms of calculations. The first thing you need to know about it is the number of wires in it determines the exact number of locations that the processor can address. So for instance, if you had a 32 wire address bus, it can address 2 to the power 32 locations, and for every wire that you add on after that, the range doubles. Now that's very similar to the calculations that you'll do in the graphics section, where if you do 2 to the power 16, you get 65,536. Now if it was address bus, that would be 65,000 locations. If it was bit depth of a graphic, that would be 65,536 colours and so on. The data bus is a bit different. It's bidirectional, and data travels in two directions. So it carries data to the processor from the devices and from the processor to the peripheral devices. And again, similar to address bus, the number of wires tells you about the function it provides. And in this case, the number of wires that are on this data bus determines the quantity of data that the bus can carry. Now that's sometimes called the word size. So for instance, a 32-bit data bus will be able to carry 32 bits of data at a time, or 4 bytes is another way to describe that. Now it's one way of improving the performance of the computer system. If you increase the number of bits or the width of the word size of a data bus, then the amount of data that can be carried per clock cycle is increased, and that's one way of increasing the performance of the computer system, because more data can be carried at the one time. The control bus has several different lines of control that you need to know the function of the operation that they provide, and those are the read, write, clock, interrupt, non-maskable interrupt, and the reset. Now we're going to talk about the read and write in more detail in another video, so I'm going to skip over those when they come up. But the first one is the clock, and the clock is simply a series of clock pulses that keep all the operations synchronized within the computer system. It's measured in hertz, and it tells you how quickly it pulses. It's like a drum beat that's continual, and it keeps on going to keep all of the operations, the things that's happening inside the processor synchronized. And again, it's another way of increasing the performance of a computer system. It's not a great indicator of how good a system performs, but it is an indicator. The speed is one thing, that will look at to see if a computer system's good. And if you to increase the clock speed, it means that operations are carried out quicker, so a faster processor will carry out operations quicker. So it's one way of improving the performance of a computer system. The interrupt, just think of an interrupt in real life. It's something that stops you doing what you were doing. So it's basically a signal to the processor from either an input device, an output device, or something that's happening. If it's trying to read memory or so on, or if the printer's out of ink. There's different types of interrupts we'll talk about in a second. And you need to know what happens when the processor deals with an interrupt. So if you think anything you're doing when you get an interrupt, you stop what you're doing, you carry out what the interrupt requires you to do, and then you go back to the task as it was before. So what happens in that case is that it stores the current state of the system that it's in. It flushes out all the registers so that they're empty. It loads the interrupt. It carries out anything the interrupt requires it to do, and then it loads the state it was in before it got the interrupt. But the one thing about interrupts to remember is that you can ignore them, you can mask them, which means simple things like maybe the printer being out of ink, the printer being out of paper and so on. You don't really want your processor to stop doing a more important task, so it's possible to ignore interrupts. Non-maskable interrupts are the exact same as interrupt, except you can't ignore them, they can't be masked, they've got to deal with them, so that's more important. Interrupts, things like file locations not being found, anything very important that would stop the current process, so it had to deal with it. Reset, depending on the colour your computer system is, now this is the blue one on these computers that I'm looking at, is basically you press it and it returns the system as if it's to its initial state. Now, not factory settings, that's completely different, as if it's just been turned on. So it clears out the registers and basically starts the computer system again as if it's just being switched on. Fetch execute cycle is something that's really important, which you're going to have to look up in the other video because it's quite a lot to it. So if you go and see the other videos, we talk about the fetch execute cycle, but basically the fetch execute cycle is where the processor gets an instruction and it decodes and executes it. And that's a read operation. If you go and look over the read operation, you'll see the fetch execute cycles attached to it there. So there we go again. Fetch execute cycles, how it talks about fetching an information, or an instruction rather, from memory and carrying out that instruction. So again, just go and check the other video and you'll see more about that. Addressability is something that we hope you remember, and that's all to do with how every piece of information stored in a unique storage location. Every address is a unique location, and that means that everyone has a unique address. Now this goes back to what you should hopefully know about binary. If you have a 1-bit address line, it would only be able to address 2 locations, the locations 0 and 1. If you increase it to 3 bits, there would be 8. And it basically goes back to what we were talking about earlier, 2 to the power of how many locations you have. Be reminded again, each storage location is capable of holding 1 word, and remember the word refers to how wide the data bus is, and it's also how many bits the processor can process in a single operation. Now those two things together allow us to calculate the total addressable memory of a computer system. So to work that out, we take the number of storage locations. To find that out, we do 2 to the power of the word the address bus times by the size of the storage location, which is the word size of the data bus. So do some examples together here. Computer system has an address bus width of 32 bits and a data bus width of 16 bits. What do we need to work out? Well, we need to work out the number of storage locations, so we do 2 to the power 32. The size of each location, 16 bits, so that would be 2 to the power 32 times 16, and we've put divided by 8 there just to put it into bytes to simplify it. So it would give us a very, very big number of bytes. When we do bytes to get it into something that's a bit simpler, we would get it converted to kilobytes by dividing by 1024. We divide kilobytes by 1024 to give us megabytes, and again by 1024 to give us gigabytes. Now the good thing about these questions in exam is they always work out to a nice round number, so if you get a decimal, you've done something wrong, so be careful with those ones. A revision task that you can do if you want to go and do it is to look up what do these different types of RAM stand for, what are they used for, but the main important ones to look up are the registers and cache and main memory, and that's what I'll talk about most just now. So the registers are the actual storage locations within the processor that are used to hold instructions whilst they're being executed, addresses that are going to be accessed, and they have immediate access, almost instantaneous access, compared to main memory, which is a lot slower. Cache is something you're always going to get asked about in the exam, and it's physically closer to the processor than main memory is. And what cache is used for is it's used to store the most commonly used instructions. And because it stores the most commonly used, and it's a much faster to access memory, it means that because they're using those instructions the most, it will speed up how quickly a computer system can access the instructions, and it will save it taking loads of time to fetch that instruction from main memory. So there's a couple of reasons why cache memory is better. It's physically closer to the processor, which saves time. It's a faster access memory than main memory, and it stores the most commonly used instructions. So it's faster at getting the most common things. So that improves the performance of the computer system as well. Main memory, we're not going into that too much because it's a bit of revision. You get RAM and ROM, and again just things we talked about there with address bus and so on. Bit of revision. What do these different types of RAM mean? Well, I'm not going to get into these too much. You can do a bit of reading. It would be useful if you knew what they were used for. So you get SRAM, static RAM, which is what's used up of cache memory. That's how the computer stores its time and date settings, and it keeps its data as long as it's got charged. DRAM, again, stands for dynamic RAM. Video RAM, a way of improving the performance of a computer system. It's RAM that's specifically set aside, and a graphics card normally, which is used to store the details that's going to be presented on the monitor and so on, which can improve your graphics display. PROM, programmable ROM, is ROM, which is kind of different from what we've learned about it in that you can change it by the user, so people can go and write instructions and so on that they want to carry out in a computer system to customize it. There's EPROM, which is the same as PROM, except you can change it, which again goes against everything we've learned about ROM. You raise it by shining a UV light onto it. This is a very important part now, measures of performance. We're going to talk about clock speed, MIPS, flops, and then application-based test, and they're kind of ordered in the reverse order of the best. So basically the best method of performance to compare computer systems is application-based tests, and clock speed the least. So what is clock speed? A wee reminder, it's pulses in second measured in megahertz. It tells you how quickly instructions can be executed. We know that clock speed increases the performance of a computer system. It gives you an idea of how quickly instructions can be carried out, so that's great. But what it doesn't take into account is the other elements that make up the computer system. It doesn't take up into consideration the speed of memory, the width of the data bus, the peripherals and so on, and it's like purely saying a car must be great because it's got a very big engine size, and not considering if it has wheels or anything else like that. So it is a good measure of system performance, but it doesn't take into account the whole system because the other peripherals, the data bus width, might not be as good to allow it to perform at the speed that it can. MIPS stands for millions of instructions per second, and that measures the number of machine code instructions that can be executed in a second, obviously. So a high number there means that it can carry out millions of instructions in a second, and that's a good method of comparison. However, it's flawed because different computer systems have different instruction sets and different ways of carrying out these instructions, so it's not fair to compare computer systems that carry out instructions in a different way. So it can be skewed if one computer system has a different instruction set than another. A more fair method of comparison is flops, which is floating point operations per second, and it basically measures how quickly a computer system can carry out floating point calculations, which is a fair method of comparison, more so than the MIPS, because the method of carrying out the calculations is similar on the different computer systems. However, again, it's not fair because it's not measuring the performance of the whole computer system. The fairest of them all is application-based tests, which use benchmarking tests that say computer system A did so well in a test, and it tells you how well other computer systems did compared to it. So that's a much fairer comparison because it takes into account all of the different parts of the computer system, and it's more quantifiable for us users rather than MIPS and flops. It's something that gives us a better indication of the whole system performance. Things that affect the performance of computer systems, the rule of thumb here is just about everything, if you increase it, improves the performance of a computer system. Now, I've already said the data bus width. If you increase the width of the data bus, it can increase the amount of data that can be carried per clock cycle, so we carry more data in the same period of time. So the data bus, increasing that, you can carry more data per clock cycle or more data at the same time. So a 2 marker that normally comes up with that question. Cache, we've already said, if you've got more cache memory, it means you can faster access to more commonly used instructions, and it's a faster access memory. If you increase the data transfer speed to peripherals, and we've now got USB 3, which is it's upwards of 500 megabits per second, that means that data can be transferred to printers and so on much quicker, which means the processor doesn't have to wait on these slow peripherals, which means that it's getting other jobs done quicker to free up to do other jobs. More main memory, that gives you more RAM, so more immediate access. It means you can store more you can run more programs at the same time, because RAM's obviously what's used when programs are being executed. So if you've got more RAM, you can either have more programs open at the same time or larger, more complex programs open at the same time. VRAM, if you increase that, then the graphics display is improved. More processors, so we're talking about multi-core processors, dual-core processors and so on. That improves system performance because the processors can work in separate tasks. So one processor can be dealing with displaying the graphics, which is kind of like a graphics card for, whilst the other processor can be worrying about sending data to our peripheral devices. And we're now seeing like quad-core processors and so on appearing in phones. Address bus width is the only thing that doesn't affect the performance of computer systems. It only increases the number of unique storage locations that you can address, so that does not improve performance of the computer system. Last wee bit is to investigate the current trends of computer systems. So what are things that if you buy a computer now and go back in 6 months' time, what will have changed? Well, things that will have changed are the clock speeds are increasing, the processors are getting faster, the main memory that it comes with is getting larger, not physically though, physically it's getting smaller in fact, but you're getting more memory, and you're getting increased back-end storage capacity in your computer systems as well. And again, just a reminder, and as a question that's come before, the clock speed has got a limit of how fast it can get. If you think when you're using your laptop, if you've got it sitting on your actual lap, you eventually start burning your legs because of how hot your processor's getting, and the faster the processor it goes, the hotter it tends to get. So it's got a limit, because at some point you're going to get to the place where it's that hot that it's going to melt other components around about it, and it's difficult to keep it cool enough to allow it to work. And again, just the trends in memory, every 6 months it tends to sort of double. Back in storage capacity, if you go and buy a digital camera just now and go back in 6 months' time, the chances are it'll be cheaper, it'll have a new model out, and the new model will have a faster processor, it'll get more back in storage capacity inside it.